Welcome, everyone. In this lesson, we're going to keep looking at investigating our derivatives of exponential and logarithmic functions. And what we're going to look at is how do we use chain rule to help us differentiate some more complicated exponential and log functions. And we're going to start with what we call the general exponential rule. And this is really just a special case. As we're going to see, this is really going to be a special case of the chain rule. All right, so let's first just remember, how do we differentiate just regular old e to the x? Well, it's really nice. The derivative of just e to the x is, well, e to the x. Really nice. It's a nice one to differentiate. And what we're going to see is, how do we differentiate something a little bit more complicated where the exponent has more going on? It's not just an x. There's more terms up there. All right, so we'll come back to this, but just to see a little example of some of the things we're going to differentiate. Let's just look at some of the functions in example 1. So all of these are all exponential functions, but there's just more going on in the exponent for all of these. So we might have something that's, it's not x, it's not just x, there's 5x, so a little bit more. Maybe we have something a little more complicated, maybe x squared plus 1 up there in the exponent, or maybe it gets way out of hand and we have something like 3x squared minus 1 over x up in the exponent. And what we're going to see is, well, how the chain rule version, to help us differentiate every single one of these. All right, so let's pop back up. And so what's going on when we look at more general exponential functions, there's more terms in the exponent. It's not just an x up there. And so when we look at a function like this, e raised to the g of x, let's kind of think about what the different parts of the function are. So we have an outer function and an inner function. And really what we have going on here is this is a composition of two functions. So our inner function is all the x terms that are up in the exponent. So if we're looking at our composition here, e to the g of x, the inner function is all of the terms up there in the exponent. So that's going to be g of x. And our outer function, well, our outer function is going to be the exponential part. So g of x is literally inside the exponent for the exponential function. So the exponential part is it's on the outside. It's the last thing that happens. And what the chain rule says is the derivative of this composition, well, if we remember back, we differentiate the outer function, we plug the inner function into that, and then we multiply by the derivative of our inner function. So let's just try this out. Let's verify the formula here. So let's differentiate f prime. And so if our outer function is just e to the x, well, the derivative of that is also just e to the x. And then let's plug in our inner function. And so wherever I see an x here, I'm just going to replace that with g of x. Oops. Wrote it twice. No, let's actually do it. Not for pretend. Let's look at these x terms wherever we see an x here, and let's actually plug in g of x. So I'm going to plug g of x here, and then I'm going to plug a g of x here. All right, and so when we're looking at this, how chain rule works is there's kind of, well, 3 steps, or there's kind of 2 things that get multiplied together. So there's the derivative of the outer function with the inner function plugged in, and that's what we just calculated. And then what we do is we multiply by the derivative of the inner function. And that's normally how we've been doing chain rule. And we've seen this with power functions before. So we're not going to go through we're not going to try to have to break this chain rule down every single time that we want to differentiate one of these exponential functions. So the way to kind of think of this is when we're differentiating an exponential function, there's two things that we end up having. So the first thing is we differentiate the outer function. So we differentiate the exponential part. And we know that when we differentiate kind of that exponential part, it just stays the same. That's the nice thing about e to the x. Derivative of e to the x just stays the same. So when we're differentiating a general exponential function, the exponential part just kind of stays the same. And then we're going to multiply by the derivative of the terms that are in the exponent. So we're going to multiply by the derivative of all the terms that we see up in the exponent. And that's really the derivative of our inner function. So when we're doing this, the e to the g of x, that's really the derivative of the outer function with the inner function plugged in, which we kind of checked by going through the decomposition. But really, it's just us differentiating an exponential function, and the exponential part just stays the same. And then we multiply by the derivative of all those terms in the exponent. And we've already seen kind of a special case of this. And these are going to be types that we see quite a bit, where the exponent terms is a constant k times x. And we called these k-forms, where k was a constant. And in this case, the derivative of e to the kx, well, the exponential part stays the same, and then we multiply by the derivative of those terms in the exponent. All right. So let's get a little practice going. Let's try some examples. All right, so let's use the general exponential rule to differentiate. Let's go through each of these. Now for this first one, this is just e to the 5x. So this is a k-form. So we could just kind of remember the process for differentiating these k-form exponential functions. But let's just try out the chain rule just to see how it works. So we're going to calculate y prime. And when we differentiate an exponential function, the exponential function basically stays the same. So we're going to have e to the 5x in our answer. And then we're going to take those terms that are in the exponent, the 5x, and we're going to multiply by its derivative. And so if I finish this up, derivative of 5x is just 5. And I kind of like putting these other terms in front. It's kind of easy once you start writing things at the end here to have those terms kind of work their way up into the exponent, or maybe having some of the exponent terms work their way down onto the main level. So to kind of keep things nice and clean and separated, I like to put all these extra terms that we're multiplying at the end kind of in front of the exponential function. All right, so there's our derivative in this case. Let's try another one. Let's differentiate y equal to e to the x squared plus 1. So we do have an exponential function, but in this case, there's more going on in the exponent. It's not just an x up there. There's a whole bunch of other stuff. So to differentiate this one, we're going to get y prime. And derivative of an exponential function, the exponential part just stays the same. So e to the x squared plus 1 stays exactly as is. We don't do anything to it. and then we take the terms that are in the exponent and we multiply by their derivative. So that's the general exponential rule. That's really chain rule. And if we clean that up, e to the x squared plus 1 times, and the derivative of x squared plus 1 is 2x. And again, I kind of like moving those extra terms, putting them in front. You know, it's not really necessary, but I think it makes it a little easier to read. So I'd write it like this. All right, try one more, just for the good practice here. So let's, again, we have an exponential function, e raised to the 3x squared minus 1 over x. And just to back up for a second, I know these are all exponential functions. Well, one, I see e, but that doesn't necessarily mean anything. What really means something here is that all of the x's, all of the variable terms, are in the exponent. That's really what makes these exponential functions. So all the variables that we have, they're all up there in the exponent. So we got to use our general exponential rule. All right, so let's start this one off. So the first thing is we differentiate the exponential function. It stays exactly the same. So the exponential part stays exactly the same. And then we multiply that by the terms from the exponent, and we want to differentiate those. All right, so that's the chain rule. That's the general exponential rule. And then we just keep going, get the derivative. So the first part here we're done with. That just stays as is. And then we're going to multiply by, well, derivative of 3x squared is 6x. And then derivative of minus 1 over x is going to be plus 1 over x squared. And again, if you don't know, or if it's not immediately obvious how to do that 1 over x, remember that we can write negative 1 over x as negative x raised to the minus 1. So when we differentiate, do a little bit of power rule, we bring down the exponent, multiply with the constant that's already in front, so it becomes positive, and then we subtract 1. So we get positive x raised to the negative 2, and I like writing things back as fractions, so 1 over x squared. And there we go. We've differentiated. Now, again, we could take all of this and move it in front of the exponential term, but you know, we got the parentheses here, so that should help keep things separated pretty well. All right, so that's differentiating exponential functions where there's more going on inside the exponential function other than just x. So we had our exponential function, but then there was other stuff inside that exponential function. Let's see what happens with log functions. So let's jump ahead in our notes here. So we're going to go on, or continue on, with our natural log function notes. And what we've seen, keep going here, where are we? What did we look at in class? Well, we did the derivative. So this is going to be important, and we'll write it down. But let's remember that the derivative of natural log is 1 over x. And what we're going to see is there's a chain rule for log functions. Just like there is for power functions and just like there is for exponential functions. And it all has to do with what the outer function actually is. All right, so let's just see an example of what these types of more complicated log functions would look like. And then we'll come back and look at the rule. So we're going to do example 2 in a little bit. Here we're going to differentiate the function y equals, and it's the natural log of x cubed plus 5x squared plus 8. So essentially what's going on here is there's more than just an x. There's a whole bunch of other stuff that's getting plugged into this natural log function. So we have essentially an outer function, natural log, and then all this stuff that's getting plugged into it. So it's really a composition of two functions. And so to differentiate something like this would take chain rule. And so if we go back, if we remember our chain rule here, it says to differentiate a composition, it's the derivative of the outer with the inner function plugged in times the derivative of the inner function. So if we're trying to differentiate something where natural log is the outer function, and let's just note that. The outer function here is natural log of all the stuff that's inside. So when we kind of break down this, we're trying to differentiate natural log of a whole bunch of x terms being plugged into that natural log function. And so to kind of look at the decomposition, the natural log part is the outer function. It's kind of the thing that happens last. And then g of x is the inner function. That's all the stuff that's getting plugged into the natural log. And so the way chain rule works is we differentiate our outer function, keep our inner function exactly the same, and then we multiply by the derivative of the inner function. And that's precisely what we're seeing here. So we start by differentiating our outer function. And really what this is just so this fraction, this first fraction that we see, 1 over g of x, why do we have that fraction? Well, it's really just the reciprocal of whatever was inside the log function. So we take all the terms that were inside the log function and we just flip them. And that's because, if we remember, derivative of natural log is 1 over x. So the way the derivative for natural log works is essentially we take the term that's inside and we flip it. We get 1 over x. It's kind of what happens. And so if we have more complicated terms inside our log function, well, the same thing's going to work. We take all those terms and we flip them, and we get 1 over all of it. All right, so this fraction right here, this is the derivative of the natural log part of our composition. And then, as usual, we have to multiply by the derivative of all those terms that are inside. And that's the second part. Differentiate inner terms. All right, so when we have a general log function where it's the natural log of a whole bunch of x terms, first thing we do is just take all the terms that were inside the natural log function and flip them. So we get this fraction. And then we take all the terms that were inside the natural log and we multiply by their derivative. And this is how we do chain rule. But we're now just looking at a special case when the outer function is a log function. So we've seen these general types of rules. We just looked at the exponential one. So the exponential one, this is when the outer function is e. So e raised to a bunch of stuff. And we've also seen the general power rule before. And for the general power rule, in that case, the outer function is raised to the power r. And so these are all these rules that we're seeing, they're really just all special cases of the chain rule, just depending on what the outer function is. So if our outer function is a power function, well, you differentiate the power function part first, and then you multiply by the derivative of all the terms inside that power function. If the outer function is an exponential, well, you differentiate the exponential part first, so it just stays the same, and then you multiply by the derivative of those terms that were inside the exponential. And same thing for log functions. So if you have a composition and the log function's the outer function, well, you differentiate the log part first, which gives you the reciprocal, and then you multiply by the derivative of those terms inside the log function. So let's give it a try with example 2. So what do we see? We see the log function, which is really the outer function, and then inside of that we have all these x terms. So we got a whole bunch of terms here inside the log function. So the outer function is natural log. So when we differentiate this, how we're going to do it is we're going to start by getting a fraction, and then we're going to multiply by the derivative of those terms that were inside the log function. All right, so let's try it. So first thing, we're going to take all the terms inside the log function and we're going to flip them. So we're going to get one big fraction here. 1 over x cubed plus 5x squared plus 8. So that's the first part. And then we take those terms and we multiply by their derivative. So what we have here is this fraction. This is the derivative of the natural log part, and then we're multiplying by the derivative of the inner function part. And then we just finish it up. So we're done with this first fraction. That's all set, no more derivatives there. And then we just finish up the differentiating here. And when we do this, just remember the parentheses. So the derivative of that is 3x squared plus 10x. And so, yeah, just remember the parentheses here, because if we left these off, if we left these parentheses off, then only the 3x squared would be multiplying this fraction. But we want the whole thing too. And that's really it. That's the general log rule. So we take the derivative of the log part, which is just the reciprocal, and then we multiply by the derivative of the inner function part. And if I wanted to clean this up, what I would probably do this is I would take all these terms and we can just move them into the numerator of this fraction. So I'd end up with 3x squared plus 10x over x cubed plus 5x squared plus 8. All right. So just some good fun using the chain rule with our log function here. And that's going to do it. So we're going to try some more examples of this in class. So we'll see you then. Bye-bye.